So let's look at a problem where they're taking this cyclohexane with a bromine attached, and they're making it into a cyclohexene with an amine attached. Notice that in this molecule, we only have one thing attached to the cyclohexane ring. And in this molecule, we've got an extra carbon attaching this amine to it. And so this is a really good problem to practice synthesis. And so how would you go about it? Well, let's think about what we need to get to make an amine first. I would say I would like to have something that looks like this with maybe a Cl on it, some acid derivative. This is where I'd like to start, but I don't have this. So I need to make this from that. And we learned that you can add carbons to a molecule using Grignard reagents. So if we have a bromine, we could, in theory, add magnesium to form this molecule, a Grignard reagent. And this molecule sort of translates to something like this. And so we need to add not only a carbon atom here, but also an oxygen atom here. And we know we can get from a carboxylic acid to an acid chloride. So maybe a better step would be to start by trying to get to a carboxylic acid. So maybe we're trying to get here. Okay, well, if I isolated just this bit here, I would have a C bonded to an O, bonded to an OH. And this is very similar to another molecule. We just have to think a little bit, but this is similar to C bonded to O, bonded to O, CO2. So can we use CO2 with this to get this carbonyl on there? And the answer is yes. This is how they do it. So we start with our bromine, our cyclohexane with a bromine on it. We add that magnesium and we form the Grignard reagent, which is in theory something with a negative charge that can go and attack something that has a partial positive charge on it. So we can attack this carbon dioxide, kicking some of these electrons onto one of the oxygens, and that is going to form, so I'm going to just scroll down a little bit, and we can form a double. So remember to read your arrows and count your carbons. So we're forming a bond. So if I'm just looking at this arrow here, that's going to be this bond to carbon. Here's my carbon from my CO2. So if I wanted to just color code the CO2 so we can keep track of where it is. Here's my C, here's my O, here's my O minus. Now I have a negatively charged species here. And if I just added H3O plus, or probably even water, this would protonate. So let's just say H3O plus. And now we can get that cyclohexane ring. We have our carbon from our CO2, double bound to an oxygen, and now we've protonated it with that H3O plus. And now we've got our carboxylic acid. Okay, how do we get carboxylic acid to a carboxylic acid derivative, Cl? Well, we can use SOCl2. So let's come over here and do SOCl2. And that's going to give us that same cyclohexane ring, our double bond, and we're going to replace the chlorine, the OH group with a chlorine group. Perfect. Now, where were we going originally? We're trying to get to this nitrogen group. Okay, so I know that if I'm looking at this molecule, I need to add this and replace the Cl of this molecule, right? And we know we can do that using aminolysis or adding that secondary amine to this compound. So I'm going to add, I'll just do it like this. I'm going to add my NH, and it's got two groups, and it's got a lone pair. That lone pair is going to attack our carbonyl carbon, kicking the electrons off of the double bond there. Okay, get our cyclohexane ring drawn, and now we're going to have an O minus, a Cl, and we've added that NH3, NH with two groups. So this should have a positive charge. Now, we can bring the electrons back down from oxygen, kick off chlorine. We'll want to lose this hydrogen too, and you could probably do that with a base. Water may even work. This is a pretty weak, it's a stronger acid than water. So let's see what we have in solution here that we could use. Okay, they use NaOH. Let's just say base, some base. I'm not going to worry too much about what it is, and we can give those electrons back to that nitrogen atom. I just did all this in one step. This probably doesn't happen in one step, but it saves a little bit of space and time. So I've still got my cyclohexane ring. I've reformed that carbonyl bond. I've gotten rid of the chlorine. I've kept my I've kept my N with its two bonds, and I have a lone pair on it again. But our starting material was an amine. It didn't have that carbonyl group. So now we have to get rid of that. And we just saw that lithium aluminum hydride will do that. And so we can sort of skip the mechanistic stuff of this, because I find that the mechanism for lithium aluminum hydride can be a bit confusing. But we know it's a reducing agent, and we know that reducing agents work by removing bonds to oxygen and replacing them with hydrogens. So we know we're going to get this N is still going to be there with its two groups, and we're going to replace one bond to oxygen with a hydrogen. We'll keep the other one, and then ultimately we're going to do the same thing twice. So we're going to get another hydrogen adding here. So this is the reduced form of this, and this is our final product. So we started with a partially made Grignard reagent, something we could form a Grignard reagent with, made the Grignard reagent. Okay. Now we needed to add another carbon to that cyclohexane ring, and we needed a carbonyl group. CO2 is a great thing to do that with. CO2 adds, you can protonate it because it's got more electrons than it wants. So you can add a hydrogen to it and make a carboxylic acid. Take that carboxylic acid, turn it into a carboxylic acid derivative or an acid halide, and then you can start adding your amine or your nitrogen group, which is an amine, and then use some base, move some electrons around, kick some things off, have a leaving group. Remember you're looking for a leaving group most of the time too. Forming this amide, reducing the amide, and that's going to give us this final product. It's a very comprehensive problem, and I think it's a good one to study.